State machines are a powerful approach to program design that can tackle almost any problem and offers a more methodical way to create a program. Formerly called finite state machines or finite state automata, these machines are constructs that are used to describe the behavior of a reactive system. Reactive systems, as opposed to transformational systems, are those systems whose inputs are not all available at a single point in time. As events occur, they trigger transitions that alter the state of the machine. State machines are useful when your code must be able to jump to any state at any time and not just execute states in the same sequence repeatedly. They offer more reactive code that can make decisions and remember the past by virtue of the current state. Basically, a finite state machine consists of a set of states and the definition of a set of transitions among those states. At any point in time, the state machine can be in only one of the possible states. It moves between states by transitions in response to events. It may be easiest to understand the concept by examining the graphical depiction known as a finite state diagram or state transition diagram of a simple example. The classic system used to illustrate a state machine is a sequential lock. The correct combination of numbers must be used to open the lock. Here's a state transition diagram for a lock whose combination is 205. Further, there must be a switch that detects whether the door is open or not. In this diagram, the bubbles are states and the arrows are transitions. If we trace the diagram, the system should begin in the locked state, and the input of a 2 on the keypad causes a transition from the locked state to the 1 right state. If 0 is typed next, the transition from 1 right to 2 right occurs. The last step is for the user to enter 5 on the keypad in order to finally arrive at the unlocked state, where in addition to the lights going from red to green, the locking mechanism is deactivated. The act of opening the door would be sensed by a switch that senses the door and would transition the system back to the locked state, switching the lights and closing the locking mechanism. There is a problem with this design. Pressing all the keys and the number pad repeatedly will eventually open the lock. We need transitions to return to the locked state when a number is pressed out of sequence. The new transitions all have the correct number with a bar above each number. This represents a logical NOT operation and simply means any number other than the correct one triggers the transition back to the locked state. For example, if the user presses 2, then 0, then 8, the machine would transition from the 2 right state to the locked state when the 8 was pressed. While this is much better, notice that the sequence 1205 would open the lock as well. If this is a problem, the transition diagram must be modified further. It might be a good idea to include a timeout feature to the lock. A timer could be added to the code that begins running when the machine enters the 1 right state. If the user does not enter the code in the set time, the timer reaching its set point triggers a transition back to the locked state. This timeout transition should be added to the diagram and therefore to the state machine as a condition for transition. At this point, you may wonder about the difference between a state transition diagram and a flowchart. A state machine represents various possible states of a system, whereas a flowchart illustrates paths the program execution can follow. A state machine includes the concept of waiting within a state, in other words, waiting for an action or event to trigger a state transition. Flowcharts do not include waiting as a concept. State machines are useful as modeling systems, while a flowchart visualizes branching sequences of a system. One difficulty in creating a program solution to a problem is the overall structure of the code. The state machine paradigm allows the problem to be broken down into sections or modules driven by the overarching state transition diagram. Here's a program I wrote to demonstrate the simple lock state machine. We'll start off on some of the basic descriptions that are pretty simple. It'll probably help to bring up the address picker. And that's not the address picker. That's the wrong commenter. There we go. In the address picker, I have already named some things. For example, I've assigned states to be just C bits. So, for example, state 1 is the locked state. So when bit C1 is on, that represents that the machine is in the locked state. When bit C2 is on, then we're in the 1 right state. So one of the buttons that needs to be pressed has been correctly pressed. It's the first button in the sequence. And then the next state, C3, is when 2 correct buttons have been pressed, and then state C4 is the unlocked state. Now, the way I've set it up is that, just like according to the state transition diagram, pressing button 2 will get us from locked to 1 right. Pressing button 0 will get us from 1 right to 2 right. Pressing the last one, which is 5 in the sequence, will get us from 2 right to the unlocked state. But then I've got a door switch also that will open and close and take us back to the locked state. Now, for reasons that will be clear later, I've also got all these next states, which are really just duplicates. If I were to expand this, you would notice that they're named identical to C1 through C4 is just C11 through C14. And I'll show later why I need those. But while we're here, let's also look at all of the inputs, and then we'll look at outputs. So for inputs, I've just simulated the 10 buttons on a keypad, 1 through, well, 9 and then 0. I chose to put them in that order just so they'd match the X1 through, X9, and the next 10 would be 0, so that's fine. But I've got a switch on X11 that is the door open switch. Okay, so there's all of our inputs, and the way I'm thinking about this is that whenever the door is closed, the switch is off, and whenever the door opens, that triggers a switch that lets you know that the door is open. So this is a normally open switch that is open as long as the door is closed. It's when the door opens up that it pushes the switch and closes it. If we go on to the outputs are pretty simple. All I've got is a red and a green light, red indicating that the door is locked, green indicating that it's unlocked, and an output to deactivate the lock. So I've got to send this a true signal, and that'll deactivate the lock and the door can swing open. So there are the various input and output devices that I've defined, and assume that I've wired up to the PLC. Now I'm going to use forces to demonstrate this in a moment, but we'll go through the code first. Now the way I've set it up is, or the way my plan was set up, is that I wanted bit C1 obviously to indicate that we're in the locked state. That's the first state. That's the state the lock should enter when it's powered up and turned on. And so what I've done is I've got a special rung here, and there's a couple things going on here, but you'll notice that there's a bit here that says first scan. This is a bit in location SC2. It's a very special bit in the PLC, and it's only true on the first scan of this program. So remember, when I turn the PLC on, this program is going to start running. It's just going to start scanning. There's probably going to be thousands of scans every second, but the only time that this instruction is true on the first rung is on that very first scan. And so I have it turn on the next state locked, and what that'll do later on, that'll actually turn us on so that we're in the state locked state. And you'll see that a little bit later. I guess I'll scroll down and show it to you now. That happens down here where I copy all of the bits from the next state to the current state. Why I have to do that, I'll explain later. For now, just know that, just think of C11 and C1 as the same thing. Okay? So basically what happens after the first scan is C1 is turned on because it got copied from C11 to C1. So now this bit here is true on rung 2. So if we consider rung 2, this rung will only compute when C1 is true. In other words, when we're in the locked state. So, like I said, after the first scan, in the second scan, C1 will be true, and that'll be the state we start in, therefore. Notice that the next rung has C2, which is not true yet, right? So C1 is the only thing that's true. And so, of course, we're not going to press the button immediately. We're looking for button 2 to be pressed. The user's not going to press it immediately. So actually what will happen is most of these rungs won't do anything, because notice that the rungs are prefaced by either C2 or C3, you see, or C4, the unlocked state. And so all of these rungs, 2, 3, and 4, won't do any, or 3, 4, and 5, won't do anything until the second rung has been triggered. So we're in the locked state. We're just waiting for button 2 to be pressed. Finally, the user comes along and presses the button. Now, you'll notice that I haven't got just a set of contacts here. I'm looking for the rising edge of the button. I'll explain why that is in just a moment. But obviously, when the user presses the button, we'll observe the rising edge. The button will go from false to true. And what that will do is that will actually reset or turn off C11 and turn on C12. Now, because the states are all copied later, what that will do is it'll cause us to calculate what the next state should be. So remember, C1 is still true, but what I've done is I've turned off C11 and turned on C12. So what will happen then is rung 3 won't execute for this scan, right? Because C2 is still not true. This rung 4, will not execute either because C3 is not true, right? And what else? Well, rung 5 won't execute because C5 is not true. But then we get to an unconditional rung where everything that's in C11 through C20 just gets copied into C1 through C10. So it's not just C11 that's copied to C1 and C20 to C10. It's the whole range. C11, 12, 13, 14, all the way through 20 is copied over into C1, C2, C3, all the way through C10. Now, why do I have to do this? It seems like, why wouldn't I just put, at the end of the rung up here, why wouldn't I just go ahead and, turn on C2 here and turn off C1? Well, the reason I don't do it is because if I turn on C2 here, the very next rung will say, oh, C2 is on. Well, is button 2 pressed? Or has there been a transition? Well, yes, there has, right? Because that's what triggered this rung 2. Button 2 has just turned on. Remember, we're still in the same scan. Now, notice that this rung indicates that, this C2 being on indicates we're in the one right state. One correct button, one right button has been pressed. And so if that's the case, then we want to see a rising edge on button 0. That's the next one in the sequence. Rather, we see that button 2 has been pressed, and so what ends up happening is we go back to the locked state. Now, I'll show you that in detail in just a moment. But let's consider what happens here. So rather than C2 coming on immediately, rather C12 comes on immediately, calculating what should be the next state, and then that gets copied down here into C1 through C10, and so C1 is off now, and C2 is on. Then we wrap back around, don't worry, I'll explain the rest of these rungs a little bit later, but we wrap back around then and continue through the scan. First rung won't do anything anymore. Remember, it only does something on the very first scan. Now the second rung doesn't do anything because now C1 is off, it's C2 that is on. Since C2 is on, this rung is computed. So C2 is on, and what that does is it starts a timer. So the very first thing that happens is we're turning on a timer. This is the timer that's going to make us go back to the locked state if it runs out of time. Now I've set it for 10 seconds. And that's probably a little bit long for a real lock, but for what I'm doing here, I needed enough time to force the inputs on and demonstrate this. So I set it for 10 seconds, and it just keeps running as long as C2 is on. So as long as we're in the C2 state, the one right state, then this timer will just keep running. Now the thing I'm looking for, like I said, the 2 has been pressed. I want to see 0, and then I want to see 5 pressed, and then I'll unlock the door. So what this is looking for, in order to go on to the next state, which is state C3, or the 2 right state, it wants to see button 0 be pressed. Button 2 has been pressed. We know that because we're in this state. We want to see button 0 pressed. And if we see that, if we see a rising edge transition on button 0, then we'll turn off the state we're in, or at least we'll compute that we need to turn off the state we're in. That's the next state 1 right there, C12, and we'll turn on next state is 2 right, you see? So C13 will be turned on, and then go down and the copy happens, we wrap back around, and life is good. On the other hand, what if the user presses 2-1, for example? Well, 1 is the wrong button. That one should not be pressed next. If they do that, then this rung is, or this portion of the rung is triggered, and what that'll do is that'll turn off. It'll say, look, we don't want to be in the one right state anymore. The user has pressed the wrong button. We need to go back to the locked state. So it turns on C11. C11 gets copied into C1, so C1 is on, and we're in the locked state, you see. Now, all this won't make a lot of sense until later when you say, well, wait a second. The state we're on determines what the outputs are, and that's something, it's a really important concept. When you're in a particular state, that state should completely control what outputs are on, what outputs are off, at least that are related to the state machine. But it's the transitions between that are driven by inputs. So basically your outputs are driven by states. The transitions themselves from state to state is driven by inputs. It's important to make that distinction between the two. So notice there's a bunch of things the user can do. They can press button number 1, button number 2, all the way through to button number 9. If they don't press button 0, we are going to transition back to the locked state. They've hit the wrong button, right? They had, 1 or 2 correct? They had 1 right. They had 2, button 2 was pressed, so they had 1 button correct, but they didn't manage to hit button 0, so we need to go back and just say, no, start over, right? We're locked. The other thing that can happen in an OR configuration here, obviously, is that the timer that we were running could expire, right? This timer, which as we're scanning through, since we're in state 1 right, or state C2, since that C2 is true, then this timer will just keep running until 10 seconds have elapsed. Once 10 seconds have elapsed, then that triggers this switch, right? Power can flow through here, and we again turn off the state we're in, which is the 1 right state, and turn on the next appropriate state, which is to simply go back to the locked state. Now let's just say that the user got the first 2 numbers right. They pressed the 2, that got us out of state C1, got us into state 2. They pressed the 0, that gets us out of state 2 and then into state 3. Obviously we turn on C13 and that gets copied into C3 later, right? They press that button and now we're in state C3, or the 2 right state. In other words, 2 of the correct buttons have been pressed in the right sequence, 2 and then 0. This rung works identically to the previous rung, except that the button we're looking for is button 5. We want to see a rising edge, a false to true transition on the button that's labeled 5. If that happens, then we can proceed to the unlocked state. That's the next state to go to, and we'll turn off the state that we're in. So you would never have C1 and C2 on at the same time, for example. None of the 2 state bits should be on at the same time, because when those bits are on, that means we're in that state. Now, so if the user presses 5, life is great. We go to the unlocked state and turn off the current 2 right state, and the door unlocks. You'll see how that happens a little later. If the user presses the wrong button, remember we wanted to see 205. If they press 201, for example, then we will turn off the state we're in and go back to the locked state. And of course, what can happen, I've got another timer here, timer T2. What can happen is if timer T2 expires, then the same thing is triggered, right? We go back to the locked state, we turn off the 2 right state. Now the last rung indicates being in the state C4, or the unlocked state. If this bit is true, if C4 is true, then we are in the unlocked state, and the only way we leave the unlocked state to go back to the locked state itself is when the door closes. So if this is a normally open switch, but when the door opens, that makes contact on the switch, so we can detect that the door is open. It's when that switch is released, when the door starts to be closed, or goes all the way to close, depending on exactly how the switch works. It's the falling edge, in other words, of that switch that I want to detect to take me back to the locked state, you see. And that's, of course, the last place to go here. Once the user has entered the correct door, or the correct code, the door will unlock and they can presumably open it. And I just want to wait and see this switch essentially cycle and see a falling edge on it in order to put the system back in the mode of the locked state and turn off the unlocked state. Now here's the copy command I've described repeatedly. Hopefully you understand how that works. But here's the interesting part. This is the last little bit. You see, what's nice about this paradigm is you program all of the inputs to transition the states, and then you program all the outputs to simply be functions of what state you're in. For example, if we're in the unlocked state, if C4 is true, then we want to deactivate the lock. Simple, right? Output Y1, that's the lock deactivate, and we want to turn on the green light, right? So I've got these as outputs, not sets and resets. Of course, when we're not in the C4 state, these will not be true. The lock will be active because we won't be outputting a signal to it, and the green light will be off, right? On the other hand, if we are not in the unlocked state, then I want the red lamp to be on. And it's that simple, right? Anytime C4 is not true, in other words, when C1, C2, or C3 are true, I want the red light to be on, right? And so notice the key here. I could have put all of this, or at least this, I could have certainly put this rung up into the rung above, rung number 5. I could have integrated those together. I chose not to because what I wanted to do is separate all of the switch input causing state transitions from being in a state which drives the outputs. And what this does nicely is it disconnects inputs from outputs, connects inputs to state transition, and connects outputs to the state that you're in. It's a really good setup, and it often works very well. This is much more powerful than just a simple sequencer because you can actually make this go to any state. You'll notice that although this is a simple example, I was able to go back to the first step, if you will, the first state, the locked state, from any state that I wish. And you could jump forward to a different state. You could certainly skip some states if you wanted to. It just depends on how you draw your state transition diagram. And one of the nice things about this is once you've got your state transition diagram drawn, then you can go and you can program based on it, and it falls out pretty easily. It separates out the problem of writing the code from designing how the thing should work. It separates all that out nicely so that you design how it should work in the state transition diagram, and then you go over and you just code it essentially. And most of the time this works very well. Most of the time this is pretty bulletproof. And so I highly recommend this approach, especially for, it doesn't have to be for your whole PLC program, but you should certainly use it for parts of your PLC program. This is a very powerful approach, and it saves a lot of the, what I call by the seat of your pants programming, where you're just throwing instructions in with ideas that seem to work a little bit, but it causes the program to break in another area. This gets by a lot of those problems, so again, I highly recommend it. Now let's demonstrate it so that you can see that this actually does work. The PLC is already running, but I'm not monitoring its running. So let's go to the status monitor, and you'll notice that we are, we are in the locked state because C1 is true. One thing you can do is you can bring up data view, and I've already set this up with all the different data I want to look at. So for example, I want to see the state bit so I can tell what state I'm in. Right now I can look very easily and see that C1 is on, and therefore I'm in the locked state. I'm not in the one write, two write, or unlocked state. I can see the next state bit calculations and see that C11 is on, C13 or 12 through 14 are off. I can see that lock deactivate is off. In other words, I'm not outputting a signal to open the lock. And the red lamp is on, the green lamp is not. Now, in order to show that this program works, what I'm going to do is bring up the override view, and I've already set it up so that I can override the particular inputs. Let's switch this around, something like this, I think, so that you can see how all of this works. So what I want to do is see the user press the correct button first. Let's try pressing the wrong one first. Let's press 1 first. So write all new values, and there we go, it's written. And what happened? Nothing. You'll notice there was a transition, right? We saw a leading edge or a rising edge on button 1, but that didn't do anything. We're still in the locked state. That didn't work. Let's turn it off. Okay, now obviously the user pressing this wouldn't see what state the lock is in, and so they wouldn't know that that's the wrong button, you see. So let's turn on button 2. Remember, that's the button that we wanted to see a rising edge on in order to move to the next state. So as soon as I write this, what will happen is it'll stop pushing button 1. We won't see that rising edge anymore, but we will see button 2 turn on. So write all values, and there we go. You see that state C2 is on, the one write state is on, the timer is running. If I don't quickly turn off button 2 and turn on button 5, I'll run out of time, and there I go. I ran out of time. Sure enough, it went back to the locked state, you see. Well, I missed it. Okay, so I can't just write all new values again. I got to turn off this button because it's the rising edge of the button that it wants to see. This time I'm going to be a little bit faster. I'm going to turn on button 2. I'm going to write all new values. It'll see a rising edge. It'll take us to the one write state, and then I'm going to quickly turn off button 2 and turn on button 5, write all new values. It'll see the rising edge then of button 5. And you know, I think actually we wanted to see 0 first, didn't we? So I've actually got these out of order. Let me change this quickly. So instead of C5, let's go for button 0, and then over here we'll go for button 5, because the code should be 205, not 250. That way I can just do it in order and it should work. Okay, so like I said, what I'm going to do is write all new values. Now everything's off. We're back in the lock state. I'm going to turn on button 2, write all new values. There we go. We're in state C2. Turn off button 2, turn on button 0, write all new values. We saw a rising edge. You'll notice that we're in state C3. Now we've hit 2 correct buttons. You can't see it, but there's another timer running. It's timer T2, running for 10 seconds, and there it is. It just finished. I timed out. I'm back in the locked state. You see how the system went back to the locked state automatically. So finally, this time I'll unlock it so you can see how this works. So I'll turn on button 2. There we go. I'll turn off button 2, turn on button 0. Before time runs out, there we are. We're in the 2 write state. Turn off button 0, turn on button 5, write all new values, and we transition now to the unlocked state. You see how bit C4 is on, indicating that the door is unlocked. You'll notice that lock deactivate is on. The green light is on, the red button or the red light is off. And you may not have noticed it, but the red light was on up until this point, right? The red light has been on the whole time until we finally reach the unlocked state. Now I can turn this off and it doesn't make any difference, right? Because the transition from the unlocked state to the locked state couldn't care less about buttons anymore. All it's looking at is the particular input, which is the door switch. And that's another nice thing about this, is that the transitions don't have to depend on all of the inputs you've got available in the system. It only depends on those inputs that are relevant for transitioning from the state you're in to the state you're interested in being in. Okay? So if I turn on the door open switch, indicating the door is being swung open, and write all new values, that won't do anything, because remember, if I scroll down in my code, what we're looking for is for the door to close, right? We want to see the falling edge on that switch. So if I turn it off and say write all new values so that it actually turns off, that should transition us back to the locked state. It does. The red lamp is back on, the lock is no longer deactivated, and the green lamp is on. And so this works very well, right? It moves around just exactly as I wanted it to. It follows the design that I made in the state transition diagram. So I highly recommend this. If you need to watch the video again, or if you need to rewind, don't feel bad, do it. This is a lot to absorb. But this nicely disconnects some things and clarifies the program and makes it sort of a modular in a sense, where you can bite off a little bit and chew it and figure out what it should do, and then it separates it out nicely so you don't have to sort of do everything at one time. An elevator is another potential application for state machines. A simple transition diagram for one includes 4 states: wait, cycle door, moving up, and moving down. Notice that states indicate action. The system begins at the wait state and transitions to any of the other 3 based on whether a request to open the door originates inside the car or a request for service outside the elevator on any floor is received. For the first case, imagine that the open door button is pressed inside the elevator. The machine transitions to the cycle door state, where it presumably opens the door, pauses, then closes the door. For the second case, imagine that a button on the current floor outside the door is pressed. Just as in the first case, the machine transitions to the cycle door state. For the third case, a button outside the elevator, either above or below the current floor, is pressed, requesting service at that floor. The system transitions to either the moving up or the moving down state as required. Note that both of these transitions also require that the elevator was already moving in the requested direction, or that there are no other requests. This is for efficient operation and servicing of passengers. Further, notice that these transitions are not simple switch inputs to the system, but require more coding as well as careful thought to decide exactly what they should depend upon. The cycle door state can move to either of the moving up or moving down states, similar to the wait state, and it transitions based on conditions that optimize the operation of the elevator. Finally, the moving states transition back to the cycle door state, since the doors must be opened when a destination floor is reached and the elevator has stopped. Programming the system to recognize when a destination floor is reached is not trivial, so more than just the state machine design is needed to accomplish full operation of the elevator. The state machine can be expanded to enhance description of the machine's operation. In this design, the acceleration and deceleration phases of motion are assigned their own states for both the upward and downward movements. Note that the transitions are not labeled for clarity. However, a bug has been introduced. The transition from the decel up and decel down states to the wait state are not right. Imagine that the elevator is coming to a stop after arriving at a floor. The doors should cycle open to allow passengers to board or disembark the elevator. Going to the wait state does not cycle the doors. Here the transitions have been fixed. A very useful feature of state machine design is that debugging can begin before the first line of code has been written. Further expanding the state machine transition diagram allows inclusion of more detail in the door operation. The cycle door state has been replaced by 3 other states: opening door, pausing, and closing door. These states clarify the operation of this section of the machine, but note that adding states to the up and down moving states did not help simplify the transitions that must occur to and from these states.